In a previous section, we defined path in a graph. Now we're going to define the distance between two vertices in a path and also consider ways to find the shortest path between two vertices. The distance between two vertices, u and v, is the number of edges in a path from u to v. Notice that this definition really depends on the path that you use from u to v. For example, if we consider the path S, A, E, then the distance from S to E is simply 2 edges between S and E. But if we choose a different path, S, B, C, and E, then the distance is 3. Now we would like to find the shortest distance between two vertices in a graph. Here in this example, we're going to use a starting vertex and find out the shortest distance between that initial vertex and all the other vertices in the graph, except vertices K, L, and M. To do that, we're going to use the breadth first search algorithm. In the algorithm, we will label each vertex with a number that represents the distance from the vertex to the starting vertex S, and the predecessor, which is the previously visited adjacent vertex. Let's begin by labeling the vertex S with 0, meaning that the distance from S to itself is simply 0. And in parentheses, we would put the predecessor, but since S is the starting vertex, there are no predecessors. Next, from the vertex S, we'll look and see two adjacent vertices, vertices A and B. And we are going to label those two vertices with the label 1 and the predecessor, which is the vertex S. We can call these vertices the first level vertices, which are vertices of distance 1 from the starting vertex. Now we go to any of these two vertices and we look for the second level vertices, which are non-labeled vertices that are adjacent. Now here there's a choice. We can go to vertex A or vertex B. Let's establish the convention here. Let's assume that we're going to follow alphabetical order when there is a choice of vertices. Alphabetically, we're going to choose A next. So we go to vertex A, and from that vertex, we find adjacent vertices that have not been labeled. In this case, we have vertex E and vertex C, and we're going to label them with 2 and the predecessor A. Now we go to the other first level vertex and we look for adjacent vertices that have not been labeled. In this case, we go to B and we look at the unlabeled adjacent vertices, which is only D in this case. And we label with 2B. Next, we continue the algorithm by visiting each second level vertex and finding adjacent vertices that have not been labeled. Now again, let's follow the alphabetical order. We have the vertices E, C, and D. So we're going to go first to vertex C and find the adjacent vertices that have not been labeled. In that case, it will be H only. We label it with 3. And the predecessor is C. Next, we go to vertex D. And we find G. We label G with 3 and predecessor D. Next, we go to vertex E and we find F. We label with 3. And we continue to do this until we label all the vertices. Here we label vertex J with 4G. And then finally, we go to H and we find vertex I and we label I with 4H. Notice that there are no more adjacent vertices that are unlabeled. Vertices K, L, and M cannot be reached, and that becomes the end of the algorithm. Now let's take a look at the labels, and we can find the shortest path from the initial vertex S to all the other vertices by just looking at the labels. So to find the shortest path from S to I, we go to vertex I and look at the labels. The labels will tell us where to go. We go backwards until we reach the starting vertex. Vertex I has the label 4H. That means we're going to select vertex H. We have vertex I and H. Then from H, we look at the label vertex C. We go to vertex C, and vertex C has label 2A. We go to A, and vertex A has label S. We go to S. So that describes the shortest path from S to I. S, A, C, H, I. Let's consider graphs where each edge has a number associated to it. Those type of graphs are called weighted graphs. The weight of a path is the sum of weights of the edges in the path. Shortest path is a path of smallest weight. We're going to consider graphs that don't have cycles with negative weight. In fact, we're going to consider weights assigned to edges that are positive. Now we introduce an algorithm called Dijkstra algorithm, which is used to find the shortest path from a vertex S to any other vertex. Here's an example of a weighted graph. Notice that each edge has a number associated to it. Then when we look at a path in a weighted graph, we can talk about the weight of the path. For example, if we have the path SAC, then the weight of this path is 5 because we add all the weights of the edges in that path. If we have another path, for example SBC, then the weight of that path is 4. Dijkstra algorithm will find a shortest path from the vertex S to any other vertex in the weighted graph. Here's how the algorithm works. Step number 1, we assign the starting vertex the label 0 and no predecessor. Here we put 0 and in parentheses dash, meaning that there is no predecessor. Step number 2, label all the other vertices as follows. The adjacent vertices are labeled with the distance from vertex S. A is adjacent to S, A then is labeled 2 and in parentheses S, meaning S is the predecessor. Vertex B is labeled 3 and in parentheses S. The other vertices that are not adjacent to vertex S are labeled with infinity and in parentheses S. The infinity here is just a symbol meaning that this is not adjacent to vertex S. So all the other vertices are labeled with infinity. Now here's step number 3. We're going to mark vertex S with a star, meaning that S now has a permanent label. That label is not going to change. As the algorithm progresses, the labels can change except the labels of the vertices that are marked with a star. And here's the table that indicates the current labels for each vertex. Vertex S has the label 0 and dash. Vertex A has the label 2S, and so forth. We keep track of the vertices that have permanent label. So far, only vertex S has a permanent label. In step 3, there is a sub-step that is very important. The next permanent labeled vertex is the one with the smallest label from the list of vertices that don't have permanent label. And here it is, 2. That's the label of A. If there is a choice between two vertices with the same smallest label, then we choose alphabetically. For example, if A had a label 2 and C had a label 2, then we would pick A. So A now is marked with a star, meaning that A now has a permanent label. That label cannot change. After that sub-step, then we look at all the adjacent vertices to that current permanent labeled vertex. We see E and we see vertex C. We can choose either one of these vertices, but let's choose alphabetically. So we continue the algorithm with vertex C. Now we look at the current label of vertex C and compare it with a candidate label. The candidate label is formed by adding the label of the current permanent labeled vertex, vertex A in this case, and 3, and that's candidate labeled 5. And we put in parentheses A because A is going to be the predecessor if we choose that candidate. And we compare the two. The old label is infinity, the candidate is 5. 5 is less than infinity, we choose 5. We're going to replace the labels. Now we go to the next adjacent vertex alphabetically. In this case, it's E. And we compare again the current label, infinity, with a candidate. The candidate is formed by adding 2 plus 1. And 3 is better than infinity. We're going to replace it. Now there are no more adjacent vertices, so we are done with A. A now is finally added to the list of permanent labeled vertices. Here we keep track of the changes. The label of C now is 5A, and label of E is 3A. Now we go back to step 3.1. We choose the smallest label from the vertices that don't have permanent labels. So we don't consider vertices S or A. Now the current smallest label is 3, but we have that for B and we have that for E. We have the choice between two vertices we're going to pick alphabetically. So we continue with B. We mark B with a star, and at B we look for adjacent vertices that don't have permanent label. Here we have C and we have D. Notice that vertex S is also an adjacent vertex, but S has a permanent label, so we don't consider S. We go to the first adjacent vertex alphabetically, that's C, and we compare the current label, which is 5A, with a candidate. The candidate is formed by the label of B plus the weight of this edge. Since 4 is better than 5, because it's smaller, we're going to replace the label 5A with 4B. At this point in the diagram, you can see that 4B is better because now we have a shortest path coming from vertex B. Previously, we had 5A, which is a path coming from the beginning, from the starting vertex, coming through A. But the path from the beginning, from vertex S, coming through B, is better, it's shorter. Now we go to the next adjacent vertex, D, and we analyze the current label, infinity, and compare with the candidate label. The candidate label is 3 plus the weight of this edge, 2, that gives us 5, and 5 is much better than infinity. Now we are done with all adjacent vertices to B. B is finally added to the list of permanent labeled vertices, and here again we keep track of the changes of the labels. Now we go back to step 3.1, and we choose the vertex that has the smallest label, and in that case is 3. Again, we choose the smallest label from the vertices that don't have permanent labels. At vertex E, we add a star, and we look for the adjacent vertices to E. We find C and we find F. Now let's go to the first one alphabetically. We look at the old label, or the current label, and we look at the candidate. The candidate now again is formed by adding the label of E, 3, plus this edge. That gives us 5. The candidate's not better than the current label, so we're not going to replace the current label. Now let's go to the next adjacent vertex, F. The current label is infinity, S, and the candidate is 11E. That's 3 plus 8. 11 is better than infinity. We're going to replace the infinity with 11E. Now E is added to the list of permanent labeled vertices. Again, back to step 3.1, we look for the vertex with the smallest label, and that's 4, and that's for vertex C. We mark C with a star. We look at the adjacent vertices to C, and that's only H. Notice that E, A, and B are also adjacent vertices, but they already have the permanent labels, so we don't consider them. At H, the current label is infinity, the candidate is 8, because it's 4 plus 4 here, and we're going to replace it because 8 is better than infinity. C is added to the list of permanently labeled vertices. Now we choose the vertex with the smallest label, that's 5, and that's for vertex D. Vertex D, we find adjacent vertex G. We're going to replace the label of G with 6D. Again, that's because it's 5 plus 1. 6 is better than infinity. D is added to the list of permanent label vertices. Again, back to step 3.1. G now has the smallest label. At G, we look and find the adjacent vertex H. At H, we compared the current label with the candidate. The candidate is 6 plus 4. We don't replace. Next, H. And at H, we find the adjacent vertex F. F, we have the current labeled, and we compare that with the candidate. 8 plus 1, that's 9, and 9 is better than 11. Finally, we choose the vertex that has the lowest label, and that's F. And at F, we don't find any adjacent vertex that does not have a permanent label. And that's the end of the algorithm. Here's the summary. Now, if we look at the labels, we can find a shortest path from vertex S to any vertex in the graph. For example, the shortest distance from S to F is 9, because if we go to vertex F, we see the label 9. The label tells us the distance from vertex S to vertex F, and that label represents the shortest distance. To find that path that gives us the shortest distance, we follow the predecessors in parentheses. From F, we go back to H. From H, we look at the label and we go back to C. From C, we go back to B, and from B, we go back to S. So A shortest path from S to F is S, B, C, H, F. One comment about Dijkstra's algorithm is that there may be another path that has the same shortest distance, but Dijkstra's algorithm will find one of them. Any other shortest path will have the same shortest distance.